into your presentations, which will be fun. So, yeah, so self-driving cars, there's a lot of stuff out there, a lot of media, a lot of news. In general, the kind of principle, right, is the challenge is to make a vehicle that can be autonomous and make decisions for itself, which means it has to do a lot of things, right? It has to be able to sense the environment around it. It has to be able to synthesize that information. It has to be able to then make decisions based on the information very quickly. And all of these things while actually taking into account the physical dynamics of the car and what the car is actually capable of doing in that time frame. So it ties together a broad range of fields, right? Because you have to have really good sensor design. You have to know what to do with that sensor information. You have to have really good understanding of the system dynamics. And then it comes down to also computer science is how fast can you make all this happen? Because it's the efficiency and the time that all of these computations take is incredibly important, because as you're rounding curves and stuff and cars are merging around and there might be pedestrians walking, it gets very challenging. And so the technology is actually very, very far already. And we're going to talk about where the field is and where the challenges are that exist right now. And hopefully, and then also this week, your reflection will be kind of on this. So we'll be leading to a time where you can kind of dig into it and think about this for yourself and what this is going to look like in the future. But my background, as I kind of shared before, is more on the control side. So I'll talk more about like where are the actual modern problems. And it turns out a lot of the problems have to do with how to sense the world, not necessarily how to actually control the vehicle, which I find pretty interesting. So a lot of the time is spent with sensing. The brief history, this is from a professor at CMU who had some kind of like chicken scratch notes on the history. So I took his notes here. But essentially, in his expertise, and he's seen a lot of this happen, his kind of take on it was that most of the primitive demos were going back to the 1920s and 30s is where this really started. And the most serious modern work was in the 1980s at CMU and Mercedes-Benz. And so CMU at Carnegie Mellon, they actually had like this van that was really ugly, and they would like drive it around, and it took so much time to like actually do all these computations. So they would drive at like 5 miles per hour, which I guess is a few kilometers per hour, maybe. So it was really, really slow. And that's because the time it took to just sense the environment and then make the actual control decisions was really, really slow, hadn't been done before. And within that time, from the 1980s to the 1990s, we actually made a lot of progress to the point that there was this challenge that was done where, I think there's also CMU, where they actually drove across the United States. 95% of it was autonomous. So they used highways, but they controlled for the braking and the throttle, but the steering was all autonomous. So it was like slightly autonomous. So 95% of it, or whatever, as how they argued, was autonomous, which is kind of funny. But that got us pretty far. So we actually, with this problem, are already most of the way there. But there's a lot of little things that take a lot of time, and really comes down to like liability and risk. If you get into an accident, who do you want to put the risk on? And we're seeing that happen with Tesla. Tesla is very close to being autonomous, but what they'll do is, and this is kind of the problem, is in the last moments before it crashed, the vehicle knows it's going to crash and it'll turn off its autopilot. And now technically the driver is responsible for the crash because they turned it off in the last few seconds, which is a little bit maybe malicious. That's kind of what's being argued. So that's kind of the thing. There's also a lot of grand challenges. If you look up like the kind of DARPA grand challenge, that's where a lot of the progress was made. And the Google car kind of happened then. And the most current efforts that are now like the form of the technology that's being used is really from the 2010s and on. So it's kind of all gotten scrapped and like replaced with more novel approaches to these challenges. But a lot of that has to do with the perception. So the general kind of like full stack of the problem, to actually make a self-driving car, you need to have perception. So you need to be able to see your surroundings, whether that's cameras or different sensors, right? That's kind of how do you actually get what you're seeing into a computer. Once you have it into a computer, you also need to have a path. So you need to be able to say, okay, where am I trying to go with my car in a kind of large scale view of a map? Then you need to know, when you have that, it's like, okay, in your immediate surroundings, what does that path look like for the next few steps? So you then make that decision. Once you have a decision of where you want the car to go, you do what's called model predictive control, which is a type of optimal control. And that actually is going to move the car and try to give the car the right torques on the wheel, or the right throttle and the right steering angle. So it's going to actually control for those two elements, how fast the wheels are going and what is the angle of the wheel. And then you're going to actually have the car move, and then you do that all over again. So this is the kind of loop. So then you have the car move, then you have the sensor sense it again, and then you go back in this problem of, okay, now where are we and where are we? What do we want our path to look like? Does it still look like we want it to look like? We adjust it. Then we calculate the new desired velocity of the wheels and the actual turning angle of the steering wheel, and then we put that back into the car and do it again. And there's a lot of different debates too. Like, so the main work has to do with perception, which we're going to talk about next time. So this time we're going to talk about everything else but perception. And it mainly has to do with perception and the sensors, because you can use a lot of stuff. You can use GPS, you can use accelerometers, you can use the cameras, which is what a lot of the main thing is cameras put on the car. That's what Tesla does. They only use cameras. You can use what's called LiDAR, which is it's like radar, but it uses light waves and bounces light waves back, forward and back to get the depth of how far things are away. And you can also use radar, which is also depth, but uses radio frequencies, which are a lot less precise. But we're going to talk about this part first and kind of where that's all, because that problem is mostly solved. Like, this part is already good enough to be used on race cars, and it's being able to be used very well for race cars. The perception part is really challenging. The perception part actually gets harder, not in a racing environment where you already have a map that not much is changing, but actually in a real world where you're driving around a city and things are really crazy. So we'll talk about this part this time, the control theory, and then we're going to talk about the perception next time. But this is how you do it. So the high-level planner is a route planning, right, with a graph search, or something that's going to give you the actual like route, general direction you want to go. And then in the actual kind of feedback loop, you would try to take that big trajectory and then make it like a local one that's closer to your car that is collision free. So something that's going to help you not crash. With that, this is just done with the actual like map. You don't actually use like any knowledge of the physics of the car. Then once you have that, you try to track that trajectory using the physics of the car and your model of the car and what it's actually going to do. And then you try to predict where it's going to go, which is all pretty much magic. So this stuff is like a lot of magic we've learned how to do, and we put it together and we have cars that can think and be for themselves, which is really fun. So the high-level planner, you can think of as Google Maps, right? Like, that's basically, you have point A, you have point B, you want to find out where to go in Brooklyn, and you get point A and B. And so now your car is like, okay, this is the general path. This is a whole fun thing in itself. If you look into how Google Maps actually works, they do a lot of optimization problems, and they do a lot of optimization and AI stuff, because they're basically trying to calculate the fastest route, right? So that's the optimization, is what route is going to get you there the quickest with all the previous information. And it turns out you can use what's called graph convolutional neural networks. So this is like the AI stuff we were talking about, but it's applied specifically to graphs, because this is essentially a graph, right? You have all these different nodes, these different road intersections, and each one of them has a value. And you can learn, it turns out, what the best kind of like route is through graph convolutional neural networks from point A to point B. So this is like the big cutting edge thing that Google is doing to improve their timing, and a lot of other like map services are using to improve their estimation of cars. At least it's a little different for like transit, of course, but for cars. So that's the high level one. The path planning, once you have this, let's say you want to decide where your car is going to go in the next 100 meters. So that's where you would use what's called a planning algorithm. And this is a whole other field that's really fun in robotics, and has been applied to autonomous driving. And this has to do with, okay, if you have an environment and a map of the environment, and you like, what is the actual best route that's going to get you there the fastest? But you want to be able to do this online, like while your robot is running. So you can do this calculation where you like calculate the distance from every possible scenario to this. Like, if you have this starting point here, and you have this endpoint here, and you want to calculate every possible scenario in the shortest path, you can do that. But remember, we have to do this online. So a lot of the focus of this is how to make algorithms that procedurally will check and start to kind of spread forward and find the route that's fastest. And like in this case, this is an obstacle you want to avoid. So it's trying to find the path that's going to get you around the obstacle. That will be the shortest path, but also be safe to avoid collision. So you're kind of trying to balance it. And there's a lot of algorithms. This is what's called A star. And that's like one of the seen as one of the best foundational techniques. There's like a bunch of research that's in this field that a lot of people do. And a lot of my friends at CMU actually like do research / work in this field, which is fun. And a lot of their capstone projects are in this field specifically of how to make these algorithms better, or like how to get their little robots to like use this and plan on the fly. And depending on what you use, right, like even in cutting edge research now, it's like very minute. So like on this left column, you see like this trajectory hugs these walls. This new one that they were like testing it against kind of doesn't like fall into this trap of hugging this wall quickly. Like it takes a more direct approach. So it's a little bit better. And you can see like the path length is smaller and the number of turns is smaller. So they're kind of showing like this approach is better because there's less turns and stuff. And then there's this other one, which is like even shorter, where it somehow gets the distance even smaller. Instead of like taking a 90-degree turn, it figures out that in this little block, you can actually go diagonally. So it's kind of trying to build logic into this path planner to find what is truly the best path. And you can do it for like different environments. This looks like an office building, so it gets more complex. So that's like the next step. So you have your big map, then you are trying to find out at every point using a algorithmic like planner, what is the actual best route for your vehicle. You do that. And this is what it looks like in kind of some context. On the left here, this is like what a lot of my friends at CMU actually did the projects on, is like this is like a small robot called a turtlebot inside of a building. And what it's trying to do is it's making these blue lines that are the actual trajectory it's trying to like test from the starting point. And then it tries to actually follow it. And it also has a sensor that's trying to map the room out and do feature detection. So this is like the problem of how do you simultaneously map out a space and plan a route at the same time, which is a pretty fun challenge. And cars kind of have to do that. The good thing with cars is that we already have really good maps of roads, so we don't have to do the mapping at the same time. So it actually makes the problem a lot simpler. If we had a map at the same time, it'd be really hard to do it quickly, but we don't. We just have to decide what route do we want, and that does get tricky because you have people moving a lot and stuff. So that's the hard part. And then this is with a robotic arm. Like if you wanted to kind of trace around and dodge this tree and not actually hit it, like maneuver right there, you can do the same thing in a 3-dimensional space, kind of in the space of the arm's ability to rotate and get around this tree. And this is a whole area of research that applies to cars, and people are still trying to figure it out. So you can dodge pedestrians. So this is an example of comparing different techniques when you have 2 people in a parking lot and you need to go around them, which is a pretty common situation, actually, it turns out, and pretty dangerous if you mess up, right? The stakes are really high. So that's all the kind of planning part. And if you have any questions, feel free to kind of throw in the chat or interrupt at any time, as usual. And the next part is kind of the actual, okay, now we know where the car is supposed to go. We know the path. How do we get it to actually follow the path? And that's the control part. So it turns out that this is the control theory side. In the control theory, this thing called model predictive control, which is the most widely utilized, what it does is it predicts a horizon into the future, and then it kind of backtracks into the closest prediction, and it just continually updates that. And so you're basically solving a small optimization problem into a very short distance in the future, and then putting that into this kind of overall flow. And so the optimizer has this model with the physics, and then it tries to optimize it, and then you see how far off it is, and it updates, it continually updates based on how far off you are. And so that's kind of the general idea. There's a lot of math, basically. This is where you do the math part. But the most important thing to figure out in this kind of control is what your model is of the actual system. And so it turns out with cars, you have a lot of options. So we can either model the car, the most basic way to model the car, well, one of the most basic ways to model the car, probably the most simple that actually works, I will say, is a bicycle model. So you pretend the car is actually just a bike with 2 wheels, and you don't worry at all about any of the actual forces in the car. All you care about, it's called a kinematic bicycle model. All you care about is the velocity of the wheel and the angle of the wheel. And you just assume, okay, everything else that happens is going to be only a function of what the angle of the wheel is and how fast the wheel is actually rotating to push us forward. And that is reasonable as long as those things are actually what you want them to be. So for most times with driving, when you put your foot down onto the throttle and the car goes forward, you actually have good control. But you can imagine there's a lot of times when you wouldn't have good control if you're slipping at all, or you're doing off-road driving, or you're driving in very like high speeds. Then these assumptions break down. But for regular driving, as long as your car is under a normal environment where the driver can act, like you can actually control the steering angle and the velocity, you can just ignore all of that and just only focus on using this type of model. And so it turns out this works really well, and it's good enough for a lot of this kind of autonomous driving for regular stuff. But it's still kind of scary because whenever you get into a self-driving car, you have to remind yourself that the model, that the math that's going on under the hood is pretending you're riding a bike, but you're not. So there's still like, it's kind of scary to think about. The reason why we do that is because it's for speed, it's for efficiency. Because the real model of a car dynamics, you'd have to factor in every wheel, and you have to factor in all the forces on each wheel and the accelerations of each wheel and the mass distribution. And the equations get a lot nastier and they scale up really quickly. And these actual values of the slips and stuff are pretty hard to calculate. It's possible, people do it, and they do it successfully, especially for racing. You have to do this. If you want to do self-driving racing, you have to use a full model of the dynamics. So it gets pretty crazy. But it just takes a lot more time. So to get it to actually converge to a solution is challenging. And when you start to do these more complicated models, you have less control over how long it takes to actually converge to a solution in your optimizer. So you kind of have that starts to become an issue, which is fun. So anyway, so most of the time this works. And but the main challenge is, right, trying to figure out which of these models, this is a big area of research, is like which of these models is actually going to give us a solution that doesn't crash, right? Seems simple enough, but if you plan a path and you have like only the red one is feasible, like this is going to give you not crashing. If you have a bad model and it's not close enough to what you want, the real system, you could drive in a way that's going to crash. And so you have to make sure your model is good enough for your car so that any error you get is not going to give you a crash, which is pretty scary. And so it turns out like people have done some research, and like this one paper I found, they were talking about how like you want to make sure that the lateral acceleration on the side of the car is lower than 0.5 times the friction coefficient. So how much friction you have on the road on a given day, which is usually like 0.7, but if it's wet, it's like 0.4 times the gravitational coefficient, the acceleration of the car downwards. And so like not perfect, but they're like, okay, as long as you're kind of in here, you get pretty much the steering that you actually get out and the velocity that you actually get out, depending on what you put in, is actually pretty accurate. So, there's some guidelines we can make to be like, all right, as long as we're not like, no one's pushing their car, you don't get hit, or you're not doing anything too crazy with your driving, you're probably fine. So that's one thing. And then people have also done experimental tests where you can build like a track, right? So they actually have a track or like a raceway, and they use the model, they simulate it, and then they actually drive the thing, and they see what the kind of difference is between the simulated version and what actually comes out from the car. So how far off are they? And this is the actual control, the velocity in the kind of forward direction of the car. And it turns out that like, it's pretty close. How close is close enough? That's the question, right? It seems right now that this model is close enough, and the car is good enough at rejecting disturbance that like the model, so this controller is pretty good at rejecting disturbances, as in, even if you have an error in your model, as long as you're close and you're within some range, it will still get you back to a desired solution. It just depends on how fast it does that. And you can see like at some of these like higher velocities where it tries to shoot for a higher velocity, it'll like miss and then it'll adjust, right? It's following the trajectory, but it's not perfect. It's kind of like bouncing around. The only danger is if you do one of these things or you quickly change velocities and your overshoot or undershoot is too much, and it causes you to perform poorly enough that you crash, then you have a problem. But it's very situational dependent. That's why this is really scary, because even though we can do this research, until we drive these cars a lot and find out when these models will fail, it's like kind of scary. And so far, like the reason they fail usually isn't this, but it's still like there's still some assumption happening, and there's still a chance it's going to fail if you break that assumption, which is something to keep in mind when you get in a self-driving car. But this is probably not what's going to give you an accident. What we talked about on Wednesday is probably what's going to cause an accident. So we'll talk about that. This is the bicycle model performing against the real thing in a circle, like how well it actually tracks a circle. And you can see it's like, it's not perfect, right? Like it kind of deviates. The red is the actual simulation, I think, or the model, and the blue is the ideal. And in this case, like it kind of cuts the corner, right? And like that's bad if all the way over here where it's cutting the corner the most on the kind of far side, where the error is kind of at a maximum. If for this maneuver you don't have that much room, then you're going to crash, right? If there's a tree right here, like you need to use a better model, or you need to take more time to make sure your optimizer is rejecting disturbance. So this is like the whole control side, and it is pretty scary. So that's like regular driving. There's a couple situations that are still unsolved in the control side. And by unsolved, I mean like we don't have a good understanding of what's going to happen. It's still being worked on. And the biggest one is merging. So anytime you have an activity where there's a highly dynamic behavior where the different cars have to interact very quickly and make decisions, that's pretty hard, because with merging, right, if you're merging into a lane, you have to see where the cars are, decide if they're going to speed up or not, and then figure out how to fit yourself. And human beings, like when we do this, we're constantly thinking about what the other car is going to do, right? We're like, are they going to speed up? Are they going to slow down? And do I have room to fit in here? And so we do all that like mental calculations, and we're actually optimizing these functions in our brain to figure out if we're going to fit or not. And if the other person, we're communicating with the other car. So somehow these cars have to do that. They have to communicate, or they have to predict what the other car is going to do. And so this becomes not only a single optimization, but now it's a double optimization where you're optimizing two cars at once. And there's ways to do this. So if you have two self-driving cars, it's pretty simple, because each car together plays what's called in this case, a Markov game, but you can do game theory basically. And I think this research paper I was reading was using like a Stackelberg game. There's different games, but it's all kind of what's called game theory, where you're searching for what's called the Nash equilibrium, where there's a point at which each side is doing its best and they're competing against each other, and neither one can do better with the other one without the other one doing worse. And so they're each kind of doing their absolute best and in equilibrium. And so that's what generally is trying to be done. It gets tricky though, is that like if you have a car merging and it's a human driver, so it's self-driving, but the other one's a human driver, then things get a little tricky, because you can't assume they want to reach equilibrium with your car. So you have to predict what they're going to do. So like the most basic way to do this, and this is what self-driving cars usually do right now, which is kind of scary, is what they do is they just assume that the other car will be at a constant velocity. And it turns out that works most of the time. And it turns out we do that too, right? You look at another car, you're like, I'm going to assume they're not going to slow down or speed up, and I'm just going to figure out what I have to do. But that's really scary, because people do slow down and speed up in reality, right? And there's plenty of times that does happen. So it does, yeah, it creates some scary stuff, especially if the merge is really fast, which there's a lot of roads, at least in the US, where that's the case. I haven't driven in Japan before, so I actually can't attest to how difficult the roads are. But they seem also pretty challenging. So yeah, this is a big area of research too, is how to make these lane changes quickly and efficiently. And there's some cool like software out there, environments that are pretty popular that people use to like specifically study this problem. And I had some classmates in my optimal control class who were working on this as well, and using this environment. And this is like a roundabout, right? And like even in this, like there's the timing is so tight, right? To decide when are you braking, when are you going to accelerate, right? You have to accelerate quickly, brake because this guy's entering, and then, you know, be ready to accelerate again. So there's just a lot of decisions that have to be made really quickly. And I mean, hopefully no one would do what this car just did and cut in front of you, but you know, people do. So it's like, what do you do when that happens? Anyways, so that's kind of the control side. Again, mostly a like solved-ish side of the problem, less of the tricky part. You can get it working most of the time, but still good to know that like these self-driving cars are going to have assumptions, and if you were to push them beyond them, like they would break. So there's probably going to be a lot of limitations on how fast they can go, what terrain they're willing to drive on, all these things, because if they go outside of that, it's going to break the physical, like the dynamics model underlying it. And if it breaks that, you're going to go into a whole host of uncertain terrain that you really don't want to be in. So something to kind of keep in mind as we use this technology. That's what's going on. Sweet. Well, that is it for this segment. And then on Wednesday, we'll talk about perception. But are there any questions on